you're falling. Right now, at this very moment, you're plummeting through a hole in space so vast that it defies human comprehension. This cosmic cavity stretches 2 billion light-years across, and you have been inside it your entire life. Your parents lived in it. Your grandparents lived in it. Every human who has ever existed has dwelt within this immense bubble of near nothingness. Scientists confirmed its existence in 2013, yet most people have never heard of it. We call it the KBC void, and its discovery has shattered some of the most fundamental assumptions we hold about our place in the universe. This is not empty space in the conventional sense. It is a region where matter itself is 20% scarcer than it should be, creating a cosmic desert that warps our measurements of reality. The universe appears to expand faster here than anywhere else, breaking our most fundamental equations and forcing cosmologists to question whether everything we think we know about the cosmos might be wrong. We will journey through the discovery that has thrown cosmology into crisis, explore why 90% of space consists of these hollow regions, and reveal what it truly means to exist in the cosmic outskirts. If you're ready to see the universe differently, hit that like button and subscribe. We begin. 3 astronomers were counting galaxies when they noticed something that should not exist. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie examined 35,000 galaxies, meticulously mapping their positions across billions of light-years of space. They were conducting what seemed like routine astronomical work, building a 3-dimensional map of our cosmic neighbourhood using near-infrared wavelengths. But as the data accumulated, an impossible pattern emerged. Everywhere they looked near Earth, there were fewer galaxies than there should be, not slightly fewer, 20% fewer. The deficit was not confined to a small region. It stretched outward in every direction for roughly 1 billion light-years, forming a spherical bubble of cosmic emptiness with Earth positioned somewhere near its centre. This was not a minor gap between galaxy clusters, the kind astronomers had observed before. This was a void on a scale that should not exist according to standard cosmological theory. The standard model of cosmology predicts that when you zoom out far enough, the universe should be roughly uniform. Sure, galaxies cluster together naturally, and empty spaces exist between them. That part makes sense. But a region this enormous, with such a significant deficit of matter, pushes the boundaries of what random chance can explain. The researchers triple-checked their data. They used multiple independent galaxy surveys. They examined the sky from different angles and different wavelengths. The result remained consistent across every test. Our galaxy and everything around it sits inside an underdense bubble of space so massive it dwarfs every other void we have ever observed. The discovery earned a name that sounds almost casual, the KBC void, using the initials of its 3 discoverers. But there is nothing casual about what it represents. This structure challenges our understanding of how the universe evolved and raises uncomfortable questions about whether the measurements we use to study the cosmos are systematically biased by our location. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty. When they do manage to create something comparable, it requires exceptionally rare initial conditions. The statistical probability of such a void existing has been calculated at less than 1 in 1,000 in some studies. Other researchers have estimated it represents a 10 sigma deviation from average density, meaning it is so unlikely that you might not find even one such void in the entire observable universe. Yet here we are, living inside one. The implications began cascading immediately through the astronomical community. If we reside in such an unusual location, does that bias every measurement we make of the cosmos? When we point our telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate? Or are we seeing a distorted local version influenced by our position inside this void? The void hypothesis offered a tantalizing answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists have measured 2 different expansion rates for the universe, depending on whether they look at the ancient cosmos or the nearby universe. The numbers disagree by 9%, which sounds small but represents a genuine crisis. Both measurements are incredibly precise. Both should give the same answer if our cosmological models are correct. They do not. If Earth sits inside a massive underdense region, the explanation becomes clear. Gravity from the denser matter surrounding the void would pull outward on galaxies within it, adding extra velocity to their motion away from us. This would make the local expansion appear faster than average. Suddenly, the conflicting measurements made sense. We're not measuring the universe incorrectly. We're measuring it from inside a hole, and that hole is affecting what we observe. This realization changed everything. But it also raised an uncomfortable question that cosmologists are still grappling with today. If our location is this unusual, can we trust anything we think we know about the cosmos? Cosmic voids are not truly empty, which makes them even stranger than their name suggests. When astronomers call a region a void, they mean it contains far less matter than the cosmic average, but matter still exists there. The void around us has roughly 15 to 20% of the normal cosmic density, depending on which studies you examine. Picture it this way. If a typical region of space contains 10 galaxies in a given volume, the same volume in our void might contain only 1 or 2. The galaxies do not vanish completely. They become rare, scattered islands in an ocean of near-nothingness. Between these lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions in the way we normally understand it. Without enough mass to pull things together effectively, structure formation essentially stops. No new galaxy clusters can form in the void's interior. No rich superclusters emerge from the sparse material. The void stays a void, and this emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant to the overall dynamics. The dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down the expansion in those areas through sheer gravitational attraction. Inside voids, gravity loses that tug-of-war decisively. Dark energy wins, driving the void to expand faster than the rest of the universe. Think of voids as bubbles in cosmic foam. They grow like soap bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. This creates a self-reinforcing cycle that amplifies over cosmic time. The more a void expands, the emptier it becomes as the sparse material within it spreads over larger volumes. The emptier it becomes, the less gravity resists dark energy's push. The result is accelerating expansion that causes voids to eat into the surrounding dense regions, claiming more territory over billions of years. Scientists have confirmed this through careful observation of galaxy motions. They measured how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the void centers faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Picture a void as a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley, but since we're talking about space rather than terrain, that pull makes galaxies fall outward, not inward, accelerating them away from the underdense region. The effect is measurable and significant. Our own galaxy is moving away from the adjacent local void at 600,000 miles per hour, driven by this gravitational imbalance. That is roughly 850 times the speed of sound, a velocity so extreme that it demonstrates just how powerful the large-scale gravitational forces are in our cosmic neighborhood. This motion is separate from the overall cosmic expansion. It is what astronomers call a peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. The interior of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space. This affects observations in subtle but important ways. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all space, they notice that light passing through voids appears slightly cooler. The reduced gravity in voids causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we observe large voids today, confirming that the voids genuinely affect light travelling through them. Understanding what makes voids empty helps explain why they matter so much to cosmology. They are not just boring blank spaces between interesting galaxy clusters. They are laboratories where dark energy dominates and where gravity takes a back seat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works. The KBC void around us might be unsettling because it makes us question our cosmic typicality, but it also offers a rare scientific opportunity. We are positioned in exactly the right place to study the universe's most extreme low-density environments from the inside. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest scale structure in nature. The web formed over billions of years as gravity amplified tiny density variations that existed in the early universe, creating an intricate network of matter and void that defines the cosmos we observe today. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly with millions of galaxies packed relatively close together, their combined gravity creating the deepest gravitational wells in the universe. Stretching between these nodes run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years. These filaments form walls, vast sheets where galaxies gather in higher than average concentrations. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure was not always obvious to astronomers. For decades, scientists photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. Distance measurements were poor. Galaxies that appeared next to each other in two-dimensional images might actually be separated by billions of light years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 1980s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. The farther away a galaxy is, the faster space carries it away from us, and the more its light shifts toward the red end of the spectrum. By combining position on the sky with redshift distance, astronomers could place each galaxy in three-dimensional space. Suddenly, the distribution snapped into focus. The universe had structure on scales nobody expected, with filaments twisting and branching like blood vessels and voids appearing as dark bubbles embedded in the network. The first major void discovery came in 1978, when two independent teams identified large underdense regions in their surveys. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, which began operations in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail. Filaments twist and branch through space. Voids appear as dark bubbles, sometimes 500 million light years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long, and supervoids like the Eridanus void that stretches 1.8 billion light-years wide, with even fewer galaxies than the KBC void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies are not the fundamental building blocks, the web itself is the structure, with galaxies just marking where the matter happens to concentrate along its filaments and nodes. This realization transformed our understanding of cosmic architecture, revealing that most of space consists not of galaxy-filled regions, but of vast empty voids separated by relatively thin walls of matter. Why does the universe organize this way? The answer reaches back to the beginning of everything. Immediately after the Big Bang, matter was not perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density. Some regions were slightly denser than average, others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even tiny advantages over cosmic time. Denser regions pulled in more matter from their surroundings, making them denser still. Less dense regions lost matter to their neighbours, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids. The cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10% but contain most of the mass. This imbalance defines the universe's character. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness punctuated by occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble, and that makes all the difference for what we observe and how we interpret the universe around us. The Milky Way is not at the centre of the KBC void, but it is close enough to matter profoundly. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual centre. That might sound like a huge distance, and it is by any human scale, but the void extends outward for 1 billion light-years in every direction from its centre, making our offset relatively small in cosmic terms. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position is not random. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments that surround it, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our entire cosmological model would be different because our vantage point would be different. Our larger cosmic neighbourhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbour Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard. It represents one of the largest gravitationally connected structures we have identified. Yet even this supercluster resides within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations in an otherwise barren expanse. The void is primarily defined by the absence of rich superclusters and large galaxy clusters at its centre. The edges of the void, where the density transitions to normal cosmic values, lie hundreds of millions of light-years away from us in every direction. Within that enormous volume, there is still plenty of matter, just not as much as there should be on average. The local group is also influenced by another nearby void called the local void, which is distinct from but connected to the larger KBC void. The local void extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It adds an extra component to our velocity through space, complicating efforts to measure the true expansion rate. Inside a supervoid like the KBC void, these peculiar velocity effects are amplified and harder to separate cleanly from the cosmic expansion signal. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions of space are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field that affects everything within it. Galaxies are not just sitting in an empty region passively expanding with the universe. They are actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light travelling through denser regions, creating subtle effects on the light's wavelength and energy. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range, roughly at the void's boundary. Beyond the shell, the universe returns to more typical density. This creates an observational bias. We are not sampling a random location in the universe. We are sampling from inside one of its most extreme features, and that affects everything we measure. Living in the void means living with systematic uncertainty about how typical our measurements really are. Every number you have ever heard about the universe's expansion rate, its age, its composition, all of these might be affected by our unusual location. We are measuring the cosmos from inside a hole, and that hole is warping our view of reality itself. Every measurement you have ever heard about the universe's expansion rate might be wrong. Not because scientists made mistakes, but because we are measuring from inside a cosmic hole that distorts the signal. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space itself expands. This number is fundamental to cosmology. It determines the universe's age, its size, and its ultimate fate. Get it wrong, and everything else collapses. One method looks at the cosmic microwave background, ancient light, from when the universe was just 380,000 years old. This light encodes information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light-years, space expands at 67 kilometers per second. This method gives us a theoretical prediction based on how the universe evolved from its earliest moments to the present day. The second method looks at nearby objects with known brightness, specifically type AYA supernovae and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be intrinsically. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists can calculate their distance. The farther away an object is, the dimmer it appears, following a simple mathematical relationship. Combining distance measurements with redshift measurements gives the expansion rate directly. Measure how fast a galaxy at a known distance is moving away, and you have the Hubble constant. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise, with very small error margins. Both should give the same answer if cosmology is correct. They do not. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance it is just random variation. The tension is real, and it is profound. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we are measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. This inflates the local Hubble constant measurement. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. This is a compelling explanation because it does not require inventing new physics or modifying fundamental theories. It simply states that we are in an unusual location, and our local measurements reflect that rather than reflecting universal properties. But here is where it gets uncomfortable. If the void explains our local measurements, then those measurements do not tell us about the universe as a whole. They tell us about our weird local environment. The cosmic microwave background method is unaffected by the void because it probes the early universe long before voids formed. That measurement might be the accurate one for the universe's global properties. This means most headlines you have seen about the universe's expansion rate might be describing a local phenomenon rather than a universal truth. Recent observations from the James Webb Space Telescope in 2024 have added new dimensions to this debate. JWST confirmed Hubble's measurements with unprecedented precision, ruling out measurement errors as the source of the tension. The measurements are solid. The discrepancy is real. But JWST data also showed that when you look at very distant supernovae, beyond the void's boundary, the inferred expansion rate begins to decrease, approaching the value predicted by the cosmic microwave background. This is exactly what the void hypothesis predicts. Other 2024 studies using gravitationally lensed supernova and baryon acoustic oscillations have provided independent confirmation. Multiple measurement techniques all point to the same pattern. The expansion rate appears higher locally and decreases with distance. The Hubble bubble, as some researchers call it, extends out to about 2 billion light-years, suspiciously close to the estimated size of the KBC void. Beyond that boundary, the universe behaves as the Standard Model predicts. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special location. The principle states that the universe should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests we are in an unusual location, which makes physicists deeply uncomfortable. Science has progressively dissented humanity from special cosmic positions over the centuries. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And now, we are supposed to believe we just happen to live inside one of the largest voids ever observed. The statistical improbability bothers many researchers, yet the evidence keeps mounting. The void exists. Our measurements are discrepant. The void's effects match the observations. Whether we like the implications or not, the universe might actually be lying to us about its expansion rate. Or more precisely, our location is causing us to misinterpret what we measure. Gravity inside a void does something profoundly counterintuitive. It pushes outward instead of pulling inward. This is not because gravity itself reverses direction. The force of gravity always attracts mass toward mass. But the geometry of a void creates an unusual situation. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley center. Inside a cosmic void, galaxies experience the same effect writ large across billions of light-years. All the matter lies outside the void in the surrounding filaments and clusters. That exterior matter gravitationally attracts the interior material, pulling galaxies outward from the void center toward the denser regions beyond. The result is an outflow, a systematic pattern of galaxies accelerating away from the underdense region. This outflow is measurable and significant. Astronomers can track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, the pattern is unmistakable. Galaxies near void centers are moving faster outward than cosmic expansion alone predicts. The effect is strongest near the void center and weakens toward the edges where matter density increases. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. Our own galaxy participates in this pattern. The Milky Way is moving at 600,000 miles per hour away from the nearby local void, driven by the gravitational imbalance. This motion combines with other local effects like the gravitational pull from the Virgo cluster to create our galaxy's overall peculiar velocity through space. The outflow has profound implications for cosmic expansion measurements. When we observe distant galaxies and measure their redshift, we are seeing a combination of two effects: the expansion of space itself and the peculiar motion of galaxies due to gravity. Normally, scientists can separate these components because peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another galaxy is moving away, and the average is zero. But inside a void, the peculiar velocities do not average out. They all point in the same direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center, but still within the void, the outflow is slower. Beyond the void's edge, the peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they are sampling this varying velocity field. If most of their supernovae lie within the void, which they do because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The farther out you measure, the less the void affects the result. This predicts that the Hubble constant should appear to decrease with distance, and recent observations from 2024 confirm exactly that trend. Modelling these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then calculate the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius with a 20% density deficit can easily produce the observed velocity anomalies. The match between predictions and observations is good enough that many researchers find the void explanation compelling. However, the standard cosmological model struggles to explain how such a large void formed in the first place. Computer simulations based on lambda-cold dark matter, our best model of cosmic evolution, rarely produce voids this extreme. When they do, it requires very specific initial conditions that are statistically unlikely. This raises a troubling possibility. Maybe our cosmological model is missing something. If voids larger and deeper than expected keep showing up in observations, perhaps structure formation works differently than standard theory predicts. Some scientists propose modified gravity theories where gravity is stronger on large scales, which would enhance structure formation and make big voids more common. Others suggest that the universe is simply more inhomogeneous than assumed, which would also make large voids less surprising. Either way, the backwards gravity in voids is telling us something important about cosmic evolution that we have not fully understood. Our motion through this gravitational landscape is faster and more complex than anyone expected, revealing dynamics that challenge our simplest models of how the universe behaves. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to shatter it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special or different from any other when you average over large regions. Isotropic means the same in all directions. The universe looks the same no matter which way you look. These assumptions simplify the mathematics of cosmology enormously, allowing scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated and predictions become much harder to make. The principle has been remarkably successful at describing many observations, but the KBC void represents a major violation of homogeneity. If the void is 2 billion light-years across with a 20% density deficit, that is a huge inhomogeneity. Even on cosmic scales, the void is not small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the center of this abnormal structure. That seems to contradict the idea that our location is unremarkable. Throughout history, science has progressively removed Earth from any special position. Copernicus showed Earth was not the center of the solar system. Later observations showed the solar system was not the center of the galaxy, and the galaxy was not the center of anything. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the center, but there is no center because every location is equivalent. The void challenges that worldview. If we live inside an abnormally large underdense region, our location is unusual by definition. Voids are common in the universe, but most are smaller than the KBC void. Supervoids this large are rare. Finding ourselves in one raises questions about whether the cosmological principle truly holds, or whether it is only approximately true on scales much larger than previously thought. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical random realization of the universe's structure, you might not find one anywhere in the observable cosmos, yet we are in one. This suggests either we are incredibly lucky, or the standard model is wrong about how structure forms. Defenders of the cosmological principle argue that the void does not actually violate the principle, because homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, which is right at the edge of where homogeneity is supposed to kick in. Maybe the universe is less smooth at those scales than we assumed, but still homogeneous on even larger scales. Alternatively, maybe the void is not as extreme as measurements suggest. different observational techniques give somewhat different density contrasts for the void. Some studies find a 20% density deficit. Others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe, though it remains a challenge for standard models. Confirming the void's exact properties requires more data, particularly deeper galaxy surveys that can map the void's extent and density profile with higher precision. Another defense is the weak anthropic principle. Perhaps intelligent life requires galaxies to form, and galaxies form preferentially in moderately dense regions rather than in the densest clusters or the emptiest voids. If most observers live in mildly underdense regions, then finding ourselves in a slight void is not surprising. We are where we are because that is where observers can exist. But this argument only works if the KBC void is not as extreme as it appears. A 20% deficit is more than mild. It pushes the boundary of what the anthropic principle can explain away. The debate over the cosmological principle is not settled. Some researchers believe the void is real and significant, requiring either modifications to cosmology or acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact or not as extreme as initially reported. Still others propose that the principle holds on even larger scales, and that the apparent violation is temporary, confined to our local region. Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict, or whether they are more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision to explain why structure forms more vigorously than predicted. If they are truly rare, we need to explain why we happen to live in one, which brings back all the philosophical discomfort about special locations that science has tried to eliminate for centuries. Frozen sound waves from the infant universe have become the most reliable ruler for measuring cosmic distances, and they confirm the KBC void's existence with remarkable precision. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were coupled together. Sound waves rippled through this plasma, creating oscillations in density much like sound waves travelling through air. When the universe cooled enough for atoms to form, the sound waves froze in place. The distance these waves travelled before freezing left an imprint on how matter is distributed today. That distance is about 490 million light-years, and it shows up as a characteristic scale in the clustering of galaxies. Astronomers can measure this scale and use it as a standard ruler, because the physics that created it is well understood. This ruler works at any distance. Whether you look at galaxies nearby or billions of light-years away, the same characteristic scale appears in their distribution. By comparing the apparent size of this scale at different distances, scientists can map how the universe has expanded over time. It is like placing identical meter sticks at various distances and measuring how big they appear. If the universe's expansion is accelerating, distant meter sticks look smaller than they should. If expansion is slowing, they look larger. The technique is called baryon acoustic oscillation analysis, and it has revolutionized distance measurements in cosmology. Unlike other methods that rely on the brightness of objects, which can be affected by dust or other complications, the baryon acoustic oscillation scale is purely geometric and robust. Using this technique, researchers have mapped the three-dimensional distribution of galaxies across billions of light-years. These maps reveal the cosmic web in unprecedented detail. They also reveal the KBC void. When scientists analyze galaxy distributions in our local region and compare them to predictions from baryon acoustic oscillations, they find a clear deficit. The void shows up as a region where the observed scale of galaxy clustering differs from what distant measurements predict. This mismatch is exactly what you expect if you're inside an underdense region. The baryon acoustic oscillations provide independent confirmation that the void exists and quantify its depth and extent. The measurements are not simple. Mapping galaxy distributions requires massive surveys that observe hundreds of thousands of galaxies and measure each one's position and redshift. Projects like the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey have spent years collecting this data. Processing it requires sophisticated statistical analysis to extract the baryon acoustic oscillation signal from the noise of random galaxy positions. The signal is subtle, typically only a few percent stronger, clustering at the characteristic scale compared to other scales. But modern surveys are sensitive enough to detect it reliably. They have measured the baryon acoustic oscillation scale at multiple cosmic epochs, tracing the universe's expansion history from when it was about half its current age to the present day. These measurements have revealed something surprising. The expansion history appears to deviate slightly from predictions based on the cosmic microwave background. The deviations are most pronounced at low redshift, meaning recent cosmic history, and they align with being inside the KBC void. Galaxies within the void show redshifts that are slightly higher than expected for their distance when using the baryon acoustic oscillation ruler. This is consistent with the outflow velocity adding to the cosmic expansion signal. The baryon acoustic oscillation measurements thus provide another piece of evidence for the void and its impact on our observations. They show that the Hubble tension is not confined to supernova measurements, but appears across multiple independent techniques. The precision of baryon acoustic oscillation measurements continues improving with new surveys. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. Recent results from 2025 show that baryon acoustic oscillation data strongly favour a void model over a void-free model, with odds of about 100 million to 1. These measurements will allow much finer mapping of the void structure and velocity field. Within the next few years, astronomers will know the void's properties to within a few percent uncertainty. That precision will either confirm the void as the explanation for the Hubble tension, or reveal additional complications that require further theoretical development. Either way, baryon acoustic oscillations are proving to be an essential tool for understanding our cosmic environment. They give us a ruler carved from the universe's earliest moments, preserved across billions of years, allowing us to measure the very fabric of space and time with astonishing accuracy. And that ruler keeps pointing to the same conclusion. We live in a hole, and that hole is affecting everything we measure. The void's existence has led some scientists to question whether gravity itself needs revision. The standard theory of gravity is Einstein's general relativity, formulated in 1915. It has passed every test thrown at it for over a century, from predicting the bending of light around massive objects to explaining the orbital decay of binary pulsars. General relativity forms the foundation of modern cosmology. But the KBC void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity and lambda cold dark matter, perhaps gravity does not work exactly as Einstein predicted on the larger scales. Some scientists propose modifying gravity rather than accepting we live in a statistically improbable location. Modified Newtonian dynamics, or MONAD, is the most prominent alternative gravity theory, proposed in 1983 by physicist Mordechai Milgram. MON suggests that gravity behaves differently when accelerations are extremely small, below a certain threshold. At high accelerations like those on Earth, or in the inner solar system, gravity follows Newton's laws and Einstein's corrections exactly. But at the tiny accelerations relevant for galaxy outskirts and cosmological scales, gravity becomes stronger than general relativity predicts. This modification was originally proposed to explain galaxy rotation curves without invoking dark matter. Galaxies spin faster than visible matter can account for. Either there is invisible dark matter providing extra gravity, or gravity itself is stronger at large distances. MOND has struggled to explain many cosmological observations, but it performs better than expected at explaining some features of the cosmic web. In MOND cosmology, structures form more efficiently, because the enhanced gravity on large scales pulls matter together more effectively. This produces richer superclusters and deeper voids compared to standard gravity. Computer simulations using MOND gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. The statistical improbability disappears. The void becomes an expected consequence of how structure forms under modified gravity. This is an attractive feature because it resolves the tension between observations and theory without invoking extreme luck. However, MOND faces serious challenges. It struggles to explain the cosmic microwave background temperature fluctuations, which standard cosmology explains beautifully using general relativity. MOND also cannot easily account for gravitational lensing observations where massive galaxy clusters bend light from background galaxies. The amount of lensing observed requires more gravity than visible matter, plus MOND's modification can provide, suggesting dark matter is still needed. Some researchers have developed hybrid models that combine MOND with a small amount of dark matter, typically in the form of neutrinos. These models, called neutrino hot dark matter cosmologies, can explain both the cosmic microwave background and the enhanced structure formation seen in the cosmic web. Another class of modified gravity theories involves changing how gravity propagates over large distances rather than changing its strength. These theories, collectively called modified gravity theories, introduce additional fields or higher dimensional effects that alter gravitational dynamics on cosmological scales while preserving general relativity's successes on smaller scales. Some of these theories predict that gravity becomes effectively stronger in low-density regions like voids, which would make large voids easier to form. Testing these theories requires precise measurements of how matter moves in voids versus dense regions. If the velocity patterns deviate from general relativity's predictions, it could indicate modified gravity at work. Recent studies in 2024 have shown that the KBC void's outflow pattern matches predictions from MOND cosmology remarkably well, while being difficult to explain in standard cosmology. The bulk flow curve, which measures how galaxies move at different distances, aligns with what MOND predicts for a void of this size. The debate between modified gravity and standard cosmology, with a statistically unlikely void, remains unresolved. Proponents of modified gravity argue that repeatedly finding structures that are too large or too rare according to standard models indicates the models are wrong. They point to the KBC void, the Shapley supercluster, the Sloan Great Wall, and other enormous structures as evidence that structure formation is more vigorous than lambda-cold dark matter predicts. Defenders of standard cosmology argue that modified gravity theories have their own problems, and that invoking them to solve one puzzle often creates new puzzles elsewhere. They prefer to accept that we live in an unusual location rather than overthrowing a century of successful gravitational physics. Future observations should help settle this debate. If large voids and extreme structures turn out to be more common than currently thought, modified gravity becomes more appealing. If they remain rare, the standard model survives but leaves us with the uncomfortable conclusion that Earth occupies a special location. Either way, the KBC void has become a battleground where fundamental physics is being tested. The void's existence forces us to reconsider either our models of gravity or our assumptions about cosmic homogeneity. Both options require major shifts in how we think about the universe, and neither is entirely comfortable. The KBC void is not alone in the universe. Other supervoids exist, some even larger, scattered through the cosmic web like bubbles in foam. The Eridanus supervoid, located in the constellation Eridanus, stretches roughly 1.8 billion light-years across, making it comparable in size to the KBC void. What makes the Eridanus supervoid particularly intriguing is how it was discovered. Astronomers did not find it by counting galaxies. They discovered it by noticing an unusually cold spot in the cosmic microwave background temperature map. This cold spot, about 10 degrees across on the sky, corresponds to a region where the microwave background is about 70 millionths of a degree cooler than average. That is much colder than typical fluctuations from the early universe. Random variations from the Big Bang should occasionally produce cold spots, but one this large and cold is rare, occurring in only about 2% of simulated universes. When astronomers surveyed the galaxy distribution in the direction of the cold spot, they found evidence for a large underdense region roughly aligned with it. Light from the cosmic microwave background passes through this void on its way to Earth, experiencing what astronomers call the integrated Sachs-Wolf effect. As the light traverses the expanding void, it loses energy, showing up as a temperature deficit. Calculations show that a void of the Eridanus supervoid's size and depth can account for about half of the observed cold spot temperature anomaly. The other half might come from a chance alignment with a cold fluctuation in the primordial cosmic microwave background, or it might indicate the void is larger and deeper than current measurements suggest. The Bhutas void, discovered in 1981, was one of the first large voids identified, sometimes called the Great Nothing. It spans about 330 million light-years across, but is not as deep as the KBC or Eridanus voids. It contains only about 60 galaxies where we would normally expect to find around 2,000. These galaxies are mostly concentrated in a tube-shaped region across the middle of the void, suggesting the void has not completely evacuated all its matter, but has pushed most galaxies to specific locations. Together, these supervoids raise important questions about cosmic structure. If both the KBC void and the Eridanus supervoid are real, and as extreme as measurements suggest, it increases the likelihood that such voids are more common than standard cosmology predicts. Two large supervoids in the observable universe might still be consistent with lambda-cold dark matter if you allow for some statistical variance. But finding 3 or 4 would become increasingly difficult to explain without modifying our understanding of structure formation. The cosmic web's full structure extends far beyond individual voids and superclusters. The web forms the largest scale organization in the universe, with filaments stretching for hundreds of millions of light years and voids occupying the vast majority of space between them. Dark matter plays the crucial role in creating this structure. Dark matter does not interact with light, making it invisible to telescopes, but it interacts gravitationally with normal matter and with itself. In the early universe, dark matter began clumping under its own gravity long before normal matter could collapse. The dark matter formed a scaffold, creating gravitational wells into which normal matter eventually fell. This process created the cosmic web we observe today, with galaxies marking where normal matter accumulated in the dark matter's gravitational landscape. The filaments of the web are essentially highways of dark matter connecting the nodes where galaxy clusters form. What voids tell us about dark energy is equally profound. Dark energy is the mysterious force accelerating cosmic expansion, making up about 68% of the universe's total energy content. In dense regions, gravity partially counteracts dark energy's push. In voids, where gravity is weak, dark energy dominates completely. This makes voids natural laboratories for studying dark energy's properties. By measuring how fast voids expand compared to predictions, scientists can test whether dark energy behaves as a constant or whether it changes in strength over time and space. If dark energy varies, that would show up as deviations from expected void expansion rates. Current measurements show that most large voids are roughly spherical, which supports the idea that dark energy is uniform, but the measurements are not yet precise enough to rule out small variations. The expansion history of voids also encodes information about dark energy. Voids have been growing for billions of years, and their current size reflects that entire history. By modelling how a void should grow over time given different dark energy properties, scientists can compare predictions to observations and constrain what dark energy must be like. Early results suggest dark energy has been roughly constant over the past several billion years, consistent with the simplest models, but ongoing studies are refining these results and looking for any deviations. Understanding the full cosmic web structure requires combining observations across many wavelengths and techniques. X-ray observations reveal hot gas in galaxy clusters. Radio observations trace neutral hydrogen in filaments. Gravitational lensing maps the distribution of dark matter. Galaxy surveys in visible and infrared light map where stars concentrate. Together, these create a comprehensive picture of the universe's architecture. The picture that emerges is one of remarkable organization on the largest scales, with the cosmic web defining where galaxies form and how they evolve. The KBC void is just one feature in this vast web, but it happens to be our feature, and studying it gives us unique insights into how the universe works. The void's existence, confirmed by multiple independent lines of evidence, challenges some of our most fundamental assumptions while opening new avenues for understanding cosmic evolution. The future of voids is one of increasing isolation, and this has dire implications for the cosmos billions of years from now. Dark energy is accelerating the universe's expansion, and that acceleration will intensify over time. Structures that are not gravitationally bound together will drift apart and eventually lose all contact with each other. This process is already happening, but it will become more extreme in the coming billions and trillions of years. Voids will expand faster than the universe as a whole because they contain less matter to resist the expansion. The filaments surrounding voids will thin out as galaxies within them are stretched farther apart by the relentless pull of dark energy. Eventually, even neighbouring superclusters will lose causal contact as space between them expands faster than light can cross. The universe's fate is increasing isolation. with structures becoming islands separated by ever-expanding voids. For galaxies within voids, this isolation will be profound. Currently, galaxies in the KBC void can still see the surrounding filaments and clusters in the distance. Light from those structures reaches us after travelling for billions of years, but as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us. The cosmic horizon, the boundary beyond which light cannot reach us before the universe expands too much, will shrink over time. Objects currently visible will fade from view as their light gets redshifted into invisibility. Galaxies deep within voids will find themselves in increasingly empty skies with fewer and fewer neighbours visible. The cosmic microwave background radiation will become cooler and dimmer as its photons stretch to longer wavelengths. Eventually, it will become undetectable. This raises a disturbing question for future civilizations. If a civilization arises in a void galaxy billions of years from now, what will they be able to learn about the universe? Their sky will be nearly empty except for their local group of galaxies. The cosmic microwave background will be too faint to detect. There will be no evidence of the Big Bang, no distant galaxies to measure cosmic expansion, no supernovae to trace acceleration. They will be cosmologically isolated, unable to observe the larger universe because light from beyond their immediate vicinity cannot reach them. Such civilizations might conclude they live in a static island universe surrounded by empty space, never suspecting the vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is the inevitable consequence of accelerating expansion driven by dark energy. Even within our own void, the long-term future looks lonely. The Milky Way and Andromeda will merge in about 4 billion years, forming a giant elliptical galaxy. This merged galaxy will be the dominant structure in our local group. But the local group itself will become increasingly isolated. Other nearby groups like the Virgo cluster will recede beyond our cosmic horizon within tens of billions of years. The merged Milky Way-Andromeda galaxy will find itself essentially alone in an expanding void. Star formation will gradually cease as gas is consumed or expelled. The galaxy will fade, containing only old red stars and eventually just white dwarfs, neutron stars and black holes. The night sky will darken as fewer stars remain active. On even longer timescales, trillions of years into the future, stars will become rare as their fuel is exhausted. Galaxies will consist mainly of dead stellar remnants slowly evaporating into space through gravitational interactions. Black holes will dominate, slowly growing by accreting whatever material remains. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass over incomprehensibly long timescales. The final state of the universe will be a diffuse sea of particles and radiation expanding forever into darkness. Voids will have consumed everything, with the last remnants of structure dissipating into the void's infinite expanse. This bleak future is billions of years away, and depends on dark energy continuing to accelerate expansion. If dark energy changes in strength or sign, the future could be different. But current observations suggest dark energy as a cosmological constant, unchanging and unrelenting. If so, the universe's ultimate fate is void domination. The cosmic web we observe today, with its intricate filaments and clusters, is a temporary phase in cosmic history. The true long-term structure of the universe is emptiness, punctuated by isolated islands of matter that grow ever more remote from each other. We live in an unusual time when the universe still has rich structure, and when voids are features within the web rather than the dominant reality. Billions of years hence, voids will be everything, and the rare islands of matter will be curiosities rather than the norm. This cosmic perspective reminds us that the universe we observe is just one snapshot in a vast evolutionary story that stretches from the Big Bang's initial fireball to the cold, dark, empty cosmos that awaits in the unimaginably distant future. Our position in time, like our position in space, affects what we can see and understand about reality. The void's existence threatens our calculations of cosmic age in ways that ripple through every corner of astrophysics. The age of the universe is one of cosmology's most important numbers, a bedrock figure that anchors our entire understanding of cosmic history. Current measurements based on the cosmic microwave background place the universe's age at 13.8 billion years. This number comes from detailed models of how the universe expanded from the Big Bang to the present, using the cosmic expansion rate measured from early universe observations, along with other parameters like matter density and dark energy density. Together, these parameters determine how long ago the Big Bang occurred. The result has been verified by multiple independent analyses and is considered highly reliable within standard cosmology. But if the local expansion rate is genuinely faster than the cosmic average due to the void, those models could be systematically wrong. Here is the problem that keeps cosmologists awake at night. If the Hubble constant measured locally, about 73 kilometers per second per megaparsec, represents the universe's true global expansion rate rather than a void-distorted local value, then the universe has been expanding faster throughout its entire history. A faster expansion rate means the universe reached its current size in less time. Running the calculations with a higher expansion rate yields a universe age of roughly 12.7 billion years instead of 13.8 billion years. That may sound like a small difference, just 8%, but it creates major conflicts with other observations that seem impossible to reconcile. The oldest stars in globular clusters appear to be about 13 billion years old based on stellar evolution theory. You cannot have stars older than the universe itself. This age paradox forces us to question either our understanding of stellar physics or our measurements of cosmic expansion. The ages of ancient stars come from understanding how stars evolve over time. Stars of different masses burn through their nuclear fuel at different rates. Low-mass stars can last hundreds of billions of years. High-mass stars exhaust themselves in just millions of years. By observing which stars have reached the end of their lives in a globular cluster, which are collections of stars that all formed at the same time, astronomers can estimate when all the stars in that cluster formed. The oldest clusters show that their most massive remaining stars are just barely still alive, indicating the clusters formed about 13 billion years ago. These measurements depend on understanding stellar physics, which is well tested through observations of countless stars but not perfect. Small uncertainties in how stars burn hydrogen, or how they evolve off the main sequence, could shift age estimates by hundreds of millions of years. Some researchers argue that if stellar ages are uncertain enough, they might accommodate a younger universe. Perhaps globular clusters are actually 12.5 billion years old, rather than 13 billion years old, which would fit with a younger universe derived from the higher local Hubble constant. But this requires assuming current stellar models are systematically wrong in just the right way, which seems contrived and unsupported by other evidence. Other scientists point out that stellar ages are not the only constraint on cosmic age. White dwarf cooling times provide an independent age measurement that does not rely on stellar evolution models in the same way. White dwarfs are the remnants of dead stars that cool gradually over billions of years, radiating away their stored heat. The coolest white dwarfs we observe have been cooling for about 12 to 13 billion years, again suggesting the universe is at least that old. These measurements do not depend on complex stellar evolution calculations, making them harder to adjust or dismiss. The age tension, like the Hubble tension from which it derives, might be resolved if the local expansion rate does not represent the global average. If the void inflates our local measurements, the cosmic microwave background estimate of 13.8 billion years could be correct for the universe as a whole. The universe would be old enough for the observed stars and white dwarfs to exist, and the apparent conflict would disappear. This resolution requires accepting that we live in an unusual location, which bothers some scientists philosophically, but it avoids requiring major changes to stellar physics or fundamental cosmology. Alternatively, both measurements could be partly right if dark energy has evolved over time. If dark energy was weaker in the past and became stronger recently, the early expansion would have been slower, and the universe would be older than the high local Hubble constant alone would suggest. This scenario is speculative and lacks direct evidence, but it remains a possibility that some researchers explore. The age issue highlights a broader problem in cosmology. Many of the parameters we measure are interconnected in complex ways. Changing the expansion rate affects not just the universe's age, but also the density of matter, the properties of dark energy, predictions for structure formation, and the timeline of cosmic history. You cannot adjust one parameter without affecting others. This makes resolving tensions difficult because fixes in one area often create problems in another. The KBC void offers a way to preserve most of the standard model by attributing discrepancies to our unusual location, but it does not eliminate the age tension completely. Some evidence for the universe's age comes from objects within the void itself. These local age measurements should be unaffected by the void's impact on expansion measurements. Yet they align more closely with the cosmic microwave background age than with the age derived from the local Hubble constant. This internal consistency within the data suggests the void explanation, while appealing, may not tell the whole story. There might be additional factors at play that we have not yet identified. Galaxies that form within cosmic voids face unique challenges and follow different evolutionary paths than their counterparts in dense environments. Understanding how void galaxies develop provides crucial insights into the role environment plays in galaxy formation and evolution. Void galaxies tend to be smaller and dimmer than galaxies in filaments and clusters. They have lower masses containing fewer stars and less overall matter. Many void galaxies are classified as dwarf galaxies, barely massive enough to hold onto their gas against the outward pressure from star formation. Their isolation means they rarely experience the galaxy mergers that are common in dense regions. Mergers are a primary driver of galaxy evolution, triggering bursts of star formation and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less developed compared to cluster galaxies. They retain characteristics that their cousins in denser environments lost billions of years ago through interactions and mergers. This makes void galaxies valuable fossils of galactic evolution, preserving states that other galaxies passed through long ago. The star formation rate in void galaxies is generally lower than in cluster galaxies, but there is a surprising twist in the data. While most void galaxies form stars slowly, a higher fraction of them are starburst galaxies experiencing intense, short-lived periods of rapid star formation. This seems paradoxical at first glance. How can galaxies in empty regions have more starbursts than galaxies in crowded areas? The answer lies in their gas content. Void galaxies are often unusually gas-rich, containing large reservoirs of neutral hydrogen that have not yet been converted into stars. In dense environments, interactions with neighbouring galaxies can strip away gas or trigger star formation that depletes the reservoir quickly. In voids, galaxies retain their gas longer because they rarely interact with neighbours. When star formation does ignite, perhaps triggered by internal processes rather than external interactions, there is plenty of fuel available. The result is an intense starburst that consumes gas rapidly before settling back into quiescence. This creates a population of gas-rich galaxies with intermittent bursts of activity scattered throughout the void. The morphology of void galaxies also differs systematically from galaxies in dense regions. Most void galaxies are late-type spirals, or irregular galaxies rather than elliptical galaxies. Elliptical galaxies form primarily through mergers, which are rare in voids. Without mergers, galaxies maintain their disk structures and spiral arms. Some void galaxies show remarkably undisturbed morphologies with smooth disk profiles and regular rotation patterns. They have not been battered by interactions or gravitational tides from neighbours, allowing them to preserve pristine structures. This makes them excellent laboratories for studying how galaxies evolve in peaceful environments. Observations of void galaxies provide a baseline for comparison with the more chaotic evolution seen in dense regions. The differences illuminate which aspects of galaxy evolution are intrinsic to the galaxies themselves versus which aspects result from environmental influences. The dark matter halos around void galaxies present another interesting feature worth examining. Dark matter dominates the mass of every galaxy, forming a halo that extends far beyond the visible stars. In voids, these halos are subject to less external gravitational influence than halos in clusters. They remain more spherical and undisturbed compared to halos in dense environments, which often get stretched and distorted by tidal forces from neighbouring halos. The simpler halo structure in voids makes them easier to model and study, providing cleaner tests of dark matter theories. However, the lowest mass halos in voids face a significant challenge that limits galaxy formation. Below a certain mass threshold, roughly corresponding to a circular velocity of 35 km per second, halos have too little gravity to retain gas efficiently. Star formation requires gas to cool and collapse, which happens more easily in deeper gravitational wells. The shallowest halos cannot form stars at all. This explains why voids are not completely filled with tiny dwarf galaxies. Below a certain mass, halos exist but remain dark, containing only dark matter with no visible galaxy to mark their location. One puzzling aspect of void galaxies that astronomers continue to investigate is their chemical composition. Stars create heavy elements through nuclear fusion, and when they die, they release these elements into space. Subsequent generations of stars incorporate these elements, gradually enriching the galaxy's overall chemical composition. This process is called chemical evolution. Void galaxies, with their slower star formation rates, should have lower chemical enrichment compared to galaxies in dense regions. Early observations seem to confirm this prediction. Void galaxies tend to have lower metallicities, meaning less abundance of elements heavier than helium, but the difference is not as large as simple models predicted. Some void galaxies show chemical abundances surprisingly similar to galaxies in normal environments. This suggests chemical evolution is more complex than the simplest models assume. Perhaps it involves gas flows in and out of galaxies that redistribute elements in ways we do not fully understand. Gas flowing into galaxies from the intergalactic medium could bring fresh material, while galactic winds driven by supernovae and star formation could eject enriched gas into space. These processes might balance in ways that make chemical evolution less sensitive to star formation history than we thought. The evolution of void galaxies over cosmic time is an active area of research. By observing void galaxies at different distances, which corresponds to different times in the past, scientists can trace how these galaxies have changed over billions of years. Early results suggest void galaxies have been relatively stable, evolving gradually without the dramatic transformations common in clusters. This stability makes them valuable for understanding the intrinsic processes that drive galaxy evolution without the complications of environmental effects. Future surveys with improved sensitivity will discover fainter void galaxies and trace their properties across billions of years of cosmic history. These observations will test whether our understanding of galaxy formation is complete, or whether void environments reveal processes we have missed by studying mainly cluster galaxies. The Laniakea supercluster is a mind-bending structure that redefines what we mean by our cosmic neighbourhood, and understanding it is crucial to grasping our position within the KBC void. Identified in 2014 by an international team led by Brent Tully, Laniakea contains roughly 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian and means immeasurable heaven, which is remarkably fitting given the scale we are discussing. The Milky Way sits on the outskirts of Laniakea, part of a vast cosmic drainage basin where galaxies flow toward a central gravitational attractor called the Great Attractor. The entire structure moves coherently, bound together by gravitational flows that override cosmic expansion on these scales. Think of Laniakea as a watershed in space rather than on a planetary surface, where matter flows downhill toward the deepest gravitational valley. Except the terrain is the curvature of space-time rather than literal landscape, and the valley is defined by the massive concentration of matter that forms the Great Attractor. The discovery of Laniakea changed how we map the universe, because it used a new definition of what constitutes a supercluster. Traditional definitions focused on regions of high galaxy density, but Tully and colleagues defined superclusters as basins of attraction, regions where galaxy motions are directed inward toward a common gravitational center. This method reveals structure that density measurements alone cannot capture. It shows not just where galaxies are, but how they move and interact gravitationally. The technique uses peculiar velocities, the motions of galaxies that result from gravity rather than cosmic expansion. By mapping these peculiar velocities across large volumes of space, astronomers can trace the gravitational flow lines that define the structure. Think of it like mapping water flow across a landscape to identify watersheds. Galaxies whose motion is controlled by Laniakea's Great Attractor belong to the supercluster. Galaxies flowing toward different attractors belong to different superclusters, even if they are right next to each other in space. Here is where the paradox emerges that connects Laniakea to the KBC void. Laniakea, despite containing 100,000 galaxies and representing one of the largest gravitationally connected structures we have identified, resides entirely within the KBC void. How can a supercluster exist inside an underdense region? The answer lies in how density is defined and measured. The KBC void is underdense compared to the cosmic average when measured over very large scales, spanning billions of light-years, but it is not uniformly empty. It contains localized concentrations of matter like Laniakea that are denser than their immediate surroundings. These concentrations are the remnants of structure formation, islands of matter that resisted draining away when the void formed. They exist as relatively dense patches within an overall underdense volume. From a large-scale perspective, averaging over billions of light years, the region is sparse. But zoom into a few 100 million light years and you find significant structure like Laniakea. This nested hierarchy of structure is common throughout the cosmic web. Voids contain filaments, which contain clusters, which contain groups, which contain galaxies, which contain stars. Structure exists at every scale, embedded within larger structures. The KBC void is primarily defined by the absence of rich superclusters and massive galaxy clusters at its center. The edges of the void, where the density transitions to normal cosmic values, lie hundreds of millions of light years away from us in every direction. Within that enormous volume, there is still significant matter, just not as much as cosmic average predicts. Laniakea occupies part of that volume. It is large compared to typical superclusters, but small compared to the void itself. The gravitational flows within Laniakea provide some of the best evidence for how gravity organizes matter on large scales. By mapping the velocities of galaxies in and around the supercluster, astronomers have constructed three-dimensional flow maps showing how matter moves through space. Galaxies closer to the great attractor are falling toward it faster. Galaxies at the edges of Laniakea are just beginning to feel its pull. These flows define Laniakea's boundaries. Everything moving toward the great attractor is considered part of the supercluster. Everything flowing away from it belongs to neighboring structures. The Milky Way's peculiar velocity points toward the great attractor, confirming we are gravitationally bound to Laniakea and will eventually, in billions of years, merge with the structures near its center. But Laniakea itself is falling towards something even larger. The Shapley supercluster, located about 650 million light-years away, is the most massive structure in our region of the universe. It contains tens of thousands of galaxies and has a gravitational pull strong enough to affect everything around it, including Laniakea. The entire Laniakea supercluster is moving towards Shapley at several hundred kilometers per second, creating a hierarchy of gravitational flows. Galaxies flow toward clusters, clusters flow towards superclusters, and superclusters flow toward even larger attractors like Shapley. The KBC void modifies these flows by adding an outward component. Galaxies are simultaneously falling toward local attractors like the Great Attractor and flowing outward away from the void center. The combination produces complex velocity patterns that astronomers are still working to fully map and understand. Understanding Laniakea's structure and motion helps clarify our position within the KBC void. We're not at the void center in complete isolation. We're offset from the center, situated in a moderately dense region that is nonetheless underdense compared to cosmic averages. Laniakea represents a significant concentration of matter within the void, but it is not enough to eliminate the void's overall underdensity. The paradox resolves when you realize that large-scale and small-scale structures coexist in complex ways. The void describes the average properties over billions of light-years. Laniakea describes the local properties over hundreds of millions of light-years. Both are real, and both matter for different aspects of cosmology. Recent studies have begun to map the connections between Laniakea and surrounding structures, revealing an even larger network of flows and attractions. The South Pole Wall, discovered in 2020, is a massive structure that wraps around Laniakea like an arm, extending the filamentary network even farther. These discoveries show that the cosmic web is more intricate than we realized, with structures nested within structures across an enormous range of scales. Our address in this web is complex. We live in the Milky Way, part of the local group, within Laniakea, inside the KBC void, which itself is embedded in the larger cosmic web that stretches across the observable universe. Each level of this hierarchy affects our observations and our understanding of cosmic structure. The cosmic microwave background radiation, that faint glow permeating all of space, holds crucial clues about the KBC void's reality and its effects on our observations. This radiation is the oldest light in the universe, released when the cosmos was just 380,000 years old, and atoms formed for the first time, allowing photons to stream freely through space. That ancient light has been traveling toward us ever since, stretched by cosmic expansion from scorching temperatures down to a frigid 2.7 Kelvin, just barely above absolute zero. The cosmic microwave background is remarkably uniform across the sky, varying by only about 1 part in 100,000 from one direction to another. But those tiny variations encode an enormous amount of information about the early universe's structure and composition. They represent the seeds from which all cosmic structure eventually grew. When astronomers map the cosmic microwave background temperature across the entire sky, using satellites like Planck, they see patterns that reveal the density fluctuations in the infant universe. Hotspots correspond to regions that were slightly denser than average. Cold spots correspond to regions that were slightly less dense. These fluctuations grew over billions of years into the galaxies, clusters, and voids we observe today. But the cosmic microwave background also reveals something else when examined carefully. It shows evidence that light has passed through cosmic voids on its journey to Earth, and these voids leave measurable imprints on the radiation. When light from the cosmic microwave background enters a void, it experiences less gravitational influence than light passing through dense regions. This creates an effect called the integrated Sachs-Wolf effect, named after the physicists who predicted it. As a photon falls into a slightly less dense region, it gains a tiny bit of energy from the gravitational potential, becoming slightly more energetic. As it climbs back out of that region, it loses energy. Normally, in a static universe, these effects would cancel perfectly, with the gain exactly balancing the loss. But the universe is not static. It expands, and that expansion is accelerating due to dark energy. During the time the photon spends crossing a void, the void itself is expanding and its gravitational potential is decreasing. This asymmetry means the photon ends up with slightly less energy than it started with, which manifests as a lower temperature when we measure it. The effect is tiny, typically only about 10 millionths of a degree, but it is detectable when you average over many voids. Astronomers have identified the locations of large voids in the nearby universe using galaxy surveys. They then look at the cosmic microwave background temperature in those directions, and find that on average, the temperature is indeed cooler than the cosmic average. The correlation is statistically significant and matches theoretical predictions. It confirms that voids do affect the cosmic microwave background through the integrated Sachs-Wolf effect, providing independent evidence that these underdense regions are real physical structures. For the KBC void specifically, the effect should be particularly strong because of the void's size. Light from the cosmic microwave background passes through nearly the entire void on its way to us, accumulating the temperature deficit over the full billion light-year extent. However, detecting this signal is challenging because the void surrounds us in all directions, making it difficult to compare temperatures inside and outside the void from our vantage point. Researchers are developing sophisticated techniques to extract the void signature from the cosmic microwave background data. One of the most intriguing features in the cosmic microwave background is the cold spot discovered by the Wilkinson Microwave Anisotropy Probe. This region is about 5 degrees across on the sky and appears roughly 100 millionths of a degree cooler than surrounding areas. It is unusually large and cold compared to typical fluctuations expected from the early universe alone. The statistical probability of such a feature arising from random early universe fluctuations is low, leading to speculation about exotic explanations. One proposed explanation is that the cold spot results from a supervoid along that line of sight, similar to the Eridanus supervoid. If a particularly large and deep void happens to lie in that direction, it could create the observed temperature deficit through the integrated Sachs-Wolf effect. Some researchers have searched for such a void in galaxy surveys and found evidence for an underdensity in that region, though the connection remains controversial. The supervoid needed to explain the cold spot would itself be statistically unlikely, creating a puzzle within a puzzle. The KBC void does not align with the cold spot. It surrounds us in all directions rather than appearing in one specific direction on the sky. Its temperature signature is therefore more subtle, showing up as a modification to the overall cosmic microwave background pattern rather than a localized anomaly. Detecting this signature requires careful modeling of what the cosmic microwave background should look like with and without the void, accounting for all the complex effects that influence the radiation's temperature. Preliminary analyses suggest the void's presence is consistent with the observed cosmic microwave background, but the signal is not yet definitive. Future measurements with higher sensitivity and more sophisticated analysis techniques should clarify whether the void leaves a detectable imprint on the cosmic microwave background temperature distribution. These measurements also constrain the void's properties. If the void were much deeper or larger than current estimates, it would create a stronger temperature signal that should already be visible in existing data. The fact that no dramatic anomaly appears in the cosmic microwave background in our direction places upper limits on how extreme the void can be. These limits are consistent with a 20% density deficit extending about 1 billion light-years, which matches other measurements from galaxy counts and velocity studies. The cosmic microwave background thus provides an independent check on the void's existence and properties, confirming through multiple lines of evidence that we live in a genuinely unusual cosmic environment. Cosmic voids are the best places in the universe to study dark energy, because they are the only regions where dark energy dominates completely, without significant competition from gravity. Dark energy is one of the most mysterious components of the universe, a force or field that causes space itself to expand at an accelerating rate. Discovered in 1998 through observations of distant supernovae, dark energy accounts for about 68% of the universe's total energy content. Yet we understand almost nothing about what it actually is or how it works. In dense regions like galaxy clusters, gravity is strong enough to resist cosmic expansion. Clusters hold themselves together gravitationally despite the universe expanding around them, and they even continue to grow by accreting matter from their surroundings. Even on slightly larger scales in filaments, gravity remains relevant, slowing the expansion of space in those regions through the collective gravitational pull of all the galaxies and dark matter concentrated there. But in voids, where matter is sparse, gravity becomes negligible compared to dark energy's influence. With no significant gravitational pull to counteract it, dark energy controls what happens in voids completely. The voids expand faster than the cosmic average, driven by dark energy's repulsive pressure acting unopposed. This makes voids natural laboratories for measuring dark energy's strength and properties, with minimal contamination from gravitational effects. By studying how voids behave, scientists can test fundamental questions about dark energy's nature. The exact nature of dark energy remains one of physics' greatest unsolved mysteries. It could be a cosmological constant, an unchanging energy density built into the fabric of space itself, as Einstein originally proposed and later abandoned. Or it could be a dynamic field that varies in strength over time and space, similar to other fields in physics like the electromagnetic field. Distinguishing between these possibilities requires precise measurements of how cosmic expansion accelerates in different environments and at different times in cosmic history. Voids provide crucial data for this investigation. In dense areas, gravity complicates everything. The local gravitational pull from nearby masses affects galaxy motions, making it hard to separate the cosmic expansion from local gravitational effects. In voids, those complications are minimal. Galaxies move almost entirely due to cosmic expansion and dark energy's influence, with only weak gravitational perturbations from the sparse matter distribution. By measuring how fast voids expand compared to theoretical predictions, scientists can test whether dark energy behaves as a constant or whether it changes. If dark energy is stronger in voids than elsewhere, or if it was different in the past compared to now, those variations would show up as deviations from expected void expansion rates. Researchers measure void expansion by tracking how the size of voids changes over cosmic time, comparing voids at different distances and therefore different cosmic epochs. The measurements are challenging because voids themselves are defined by the absence of bright galaxies, making them inherently difficult to observe directly. Another way voids help study dark energy is through their shape. Dark energy affects not just how fast the universe expands, but also how it expands in different directions. If dark energy is truly uniform throughout space, voids should expand equally in all directions, maintaining spherical or nearly spherical shapes. But if dark energy has variations, or if there are other unknown forces at work, voids might expand more in some directions than others, becoming elongated or distorted. Observations of void shapes can therefore reveal whether dark energy is uniform or has structure. Current measurements show that most large voids are roughly spherical within observational uncertainties, which supports the idea that dark energy is uniform. But the measurements are not yet precise enough to rule out small variations. Improved surveys in the coming years will provide much better shape measurements. allowing tighter constraints on dark energy's properties. The expansion history of voids encodes information about how dark energy has evolved over cosmic time. Voids have been growing for billions of years, and their current size reflects that entire history. By modelling how a void should grow over time given different dark energy properties, scientists can compare predictions to observations and constrain what dark energy must be like. If dark energy was weaker in the past and became stronger recently, voids would have grown slowly at first and then accelerated their expansion. If dark energy has been constant, voids should grow at a steady accelerating pace determined by that constant value. Observations of voids at different distances, which corresponds to different times in cosmic history, allow testing these scenarios. One particularly useful technique involves measuring void edges, the boundaries between voids and surrounding filaments. This boundary is a transition zone where density rises sharply from the void's sparse interior to the filament's denser material. The boundary evolves over time as matter drains out of the void and accumulates in the filaments. The sharpness and location of this edge depends on how fast the void is expanding, which in turn depends on dark energy's strength. By mapping void edges at different cosmic times and comparing them to simulations, researchers can infer how dark energy has influenced void growth over billions of years. Early results suggest dark energy has been roughly constant over the past several billion years, consistent with the simplest cosmological constant models. But ongoing studies are refining these results and looking for any deviations that might hint at more complex behaviour. If dark energy is found to vary with time or space, that would revolutionise our understanding of fundamental physics and require new theories to explain the phenomenon. Even confirming that dark energy is constant and uniform would be scientifically valuable because it would rule out many alternative theories and narrow the search for dark energy's physical origin. The KBC void, being the largest and closest supervoid, offers the best opportunity for detailed dark energy studies. Its proximity allows measurements that are impossible for distant voids. Galaxies within the void can be observed individually and their properties studied in detail. The void's velocity field can be mapped with high precision. Its density profile can be measured at multiple scales. All of this data helps constrain dark energy models and test whether the observed void behavior matches theoretical predictions. Recent analyses have shown that the KBC void's expansion is consistent with standard dark energy models within current measurement uncertainties. But as observations improve, any deviations from predictions would provide crucial clues about dark energy's true nature. The void gives us a unique cosmic laboratory where dark energy operates unimpeded, allowing us to study this mysterious force in its purest form and potentially unlock one of the universe's deepest secrets. Understanding how astronomers actually discovered and mapped the KBC void reveals the remarkable technological achievements that have transformed our understanding of cosmic structure. The discovery did not happen with a single observation or a single telescope. It required decades of technological development, multiple independent surveys, and sophisticated data analysis techniques that pushed the boundaries of what was computationally possible. The journey began with galaxy redshift surveys in the 1970s and 1980s. These early surveys used spectroscopy to measure the wavelengths of light from thousands of galaxies, determining their distances by measuring how much cosmic expansion had stretched their light. The CFA redshift survey and subsequent projects painstakingly measured galaxy positions one at a time, slowly building three-dimensional maps of the nearby universe. Each observation required hours of telescope time, and the resulting catalogues contained only thousands of galaxies. These pioneering efforts revealed hints of large-scale structure, including the first major voids discovered in 1978, but they lacked the depth and breadth needed to identify something as massive as the KBC void. That required a quantum leap in observational capability that came with the 2-micron all-sky survey, or 2MASS, which operated from 1997 to 2001. This survey used near-infrared light to catalogue over 300 million objects, including stars and galaxies across the entire sky. Near-infrared observations have a crucial advantage over visible light surveys. Dust in our galaxy and between galaxies absorbs and scatters visible light, obscuring our view of distant objects. But near-infrared light penetrates dust much more effectively allowing astronomers to see galaxies that would be invisible in optical surveys. This wavelength choice was critical for mapping the large-scale structure accurately because it reduced selection biases caused by dust extinction. The two-mass data provided the foundation for Keenan, Barger and Cowie's analysis. They combined two-mass observations with other surveys to create a comprehensive three-dimensional map of galaxy positions, extending out to distances of several billion light-years. But raw galaxy positions are not enough. Astronomers needed to convert sky positions and redshifts into actual three-dimensional coordinates, accounting for the geometry of an expanding universe and various observational effects. This required sophisticated analysis pipelines that could process hundreds of thousands of galaxy measurements, apply corrections for dust extinction, account for the selection function of the survey, which describes what types of galaxies the survey could and could not detect, and statistically analyze the resulting distribution to identify significant density fluctuations. The computing power needed for this analysis only became available in the early 2000s, making the KBC Void's discovery possible only in the modern era of big data astronomy. The team used multiple statistical techniques to characterize the underdensity they observed. They calculated correlation functions that measure how galaxy density varies with distance from a given point. They performed Fourier analysis to identify structure on different spatial scales. They compared their observations to mock catalogues generated from cosmological simulations to assess the statistical significance of the void. Every analysis pointed to the same conclusion: a massive underdensity surrounding our cosmic neighbourhood. Confirming the discovery required independent verification using different datasets and different methods. Other research groups analysed data from the Sloan Digital Sky Survey, which had been systematically mapping the universe since 2000. SDSS used a different telescope, different instruments, and different target selection criteria, making it an ideal independent check. When SDSS data was analysed for local structure, it confirmed the existence of an underdensity consistent with the KBC void, though different groups measured slightly different sizes and depths. Additional confirmation came from X-ray surveys conducted by satellites like Rosat and XMM Newton. These observatories map the distribution of hot gas in galaxy clusters, which traces the densest regions of the cosmic web. When researchers examined X-ray maps of our local universe, they found a deficit of galaxy clusters within the volume identified as the KBC void, providing independent evidence from a completely different wavelength regime. The technology continues to improve. Modern surveys like the Dark Energy Spectroscopic Instrument, which began operations in 2021, can measure redshifts for tens of millions of galaxies with unprecedented precision. DESY uses robotic fiber positioners to observe 5,000 galaxies simultaneously, allowing it to map cosmic structure faster and more completely than any previous survey. Early DESY results released in 2024 and 2025 have provided the most detailed maps yet of the void structure and confirmed its basic properties with higher confidence than ever before. Space-based observatories have also contributed crucial data. The Planck satellite mapped the cosmic microwave background with exquisite precision, revealing subtle temperature variations that encode information about the density distribution along different lines of sight. When Planck data is combined with galaxy surveys, it provides additional constraints on the void's depth and extent. The James Webb Space Telescope, launched in 2021, has begun observing distant galaxies with unprecedented clarity, allowing astronomers to trace how structure has evolved over cosmic time and compare void properties at different epochs. Future technology promises even more revelatory discoveries. The Vera Rubin Observatory, scheduled to begin operations in 2025, will use the largest digital camera ever built to photograph the entire visible sky every few nights. Over a decade, it will create an incredibly detailed time-lapse movie of the universe, discovering hundreds of millions of new galaxies and mapping the cosmic web in 3 dimensions with unprecedented completeness. The Euclid Space Telescope, launched in 2023, is specifically designed to map dark matter distribution and measure the properties of dark energy by studying how galaxies cluster and how light bends around massive structures. These next-generation instruments will refine our understanding of the KBC void dramatically. They will measure its density profile with higher precision, trace its velocity field in greater detail, and determine whether it is truly as unusual as current measurements suggest. They will discover and characterize other supervoids throughout the observable universe, allowing statistical comparisons that can test whether the KBC void is genuinely rare or just one of many such structures that we have not yet found. The technology that revealed the void's existence continues to evolve, promising answers to questions we could not even ask a generation ago. Not all scientists agree on the KBC void's interpretation, size, or even its existence as a distinct structure. The scientific debate surrounding the void reveals how astronomers grapple with ambiguous observations and competing theoretical frameworks. Understanding these alternative perspectives is crucial for appreciating the full complexity of the situation and the challenges inherent in cosmic structure analysis. Some researchers argue that what we call the KBC void is actually a collection of smaller overlapping voids rather than a single coherent supervoid. In this view, the apparent large-scale underdensity results from the superposition of multiple moderate-sized voids that happen to align along our line of sight in most directions. This interpretation would make the structure less statistically improbable, because smaller voids are much more common in standard cosmological simulations than supervoids the size of the KBC void. The distinction matters for both statistical arguments and physical interpretation. A collection of smaller voids would be easier to explain within lambda-cold dark matter without requiring exceptional initial conditions. It would reduce the apparent violation of the cosmological principle, because we would not be claiming to live in an extraordinarily rare structure, just in a region where several ordinary structures happen to overlap. However, detailed analyses of the density profile and velocity field suggest the underdensity is smoother and more coherent than the multiple void hypothesis would predict. Other scientists question whether the density deficit is as large as 20%. Different measurement techniques yield different results, with some analyses finding deficits closer to 10 or 15%. This variance arises from systematic uncertainties in converting galaxy counts to mass density, accounting for survey selection effects, and defining the void's boundaries. If the true deficit is on the lower end of these estimates, the void becomes less extreme and less statistically problematic, though still significant. The boundaries of the void are particularly contentious. Unlike a planet or star with a well-defined edge, cosmic voids fade gradually into their surroundings. Deciding where the void ends and normal density begins is somewhat arbitrary and depends on how you define the threshold. Different research groups use different criteria, leading to estimates of the void's radius ranging from about 300 megaparsecs to over 700 megaparsecs. This factor of 2 uncertainty in size translates into order of magnitude uncertainty in volume and total mass deficit. Some alternative models propose that the apparent underdensity is not a true void, but rather an artifact of how we measure distances. If there are systematic errors in supernova distance measurements, or peculiar velocities that we have not properly accounted for, the inferred galaxy distribution could be distorted in ways that create the illusion of a void where none exists. This possibility seems increasingly unlikely as independent distance measurement techniques continue to confirm the basic result, but it remains a logical possibility that some researchers explore. Another competing interpretation suggests that the underdensity is real, but not spatially localized around us. Instead, it might be a temporal feature affecting the entire observable universe at the current epoch. In this scenario, the whole universe might be less dense than the cosmic microwave background predicts, perhaps due to some modification in how structure formed or evolved. This would remove the problem of our location being special, but it would require even more dramatic revisions to cosmology than the local void hypothesis. The debate also extends to the void's impact on cosmological measurements. While many researchers find the void hypothesis compelling as an explanation for the Hubble tension, others argue that the void's effects are too small to fully account for the observed discrepancy. Detailed calculations of how a void affects redshift measurements depend on assumptions about the void's density profile, velocity field, and exact geometry. Different assumptions yield different predictions, and not all of them can fully resolve the 9% difference between local and global Hubble constant measurements. Some alternative explanations for the Hubble tension do not invoke the void at all. These include proposals for new physics in the early universe, such as additional energy injection after recombination, modifications to neutrino physics, or interactions between dark matter and dark energy. Each of these alternatives faces its own challenges and requires evidence beyond just fixing the Hubble tension. But they remain viable possibilities that some researchers prefer to the void-based explanation. There is also debate about whether the void's effects on expansion measurements can be cleanly separated from other local peculiarities. Our cosmic neighbourhood contains several unusual features beyond just the void, including the local sheet, the zone of avoidance where our view is obscured by the Milky Way's disk, and the great attractor whose mass and location are not perfectly constrained. These features create a complex local gravitational environment that affects measurements in ways that are difficult to model precisely. Recent work has attempted to disentangle these various effects using sophisticated simulations and statistical analyses. The results suggest that the void is indeed the dominant local feature affecting expansion measurements, but uncertainties remain large enough that alternative interpretations cannot be definitively ruled out. This is the nature of cutting-edge science operating at the limits of observational precision. Multiple competing hypotheses remain viable, and resolving between them requires better data and more refined theoretical models. The scientific process thrives on this kind of healthy debate. Researchers on different sides of these arguments are not arguing about trivial matters or engaging in academic point scoring. They're genuinely trying to understand what the observations tell us about the universe's structure and our place within it. The fact that multiple interpretations remain plausible reflects both the complexity of cosmic structure and the remaining limitations in our observational capabilities. As data improves and theoretical understanding deepens, some of these alternatives will be ruled out while others may gain support. The KBC void forces us to confront profound philosophical questions about our place in the cosmos and the nature of scientific observation itself. These questions go beyond mere technical details of cosmology to touch on fundamental issues that have occupied philosophers and scientists for centuries. Understanding these implications helps us appreciate why the void's discovery is so unsettling to many researchers, even those who accept its reality. The cosmological principle is not just a mathematical convenience. It embodies a deep philosophical commitment that has guided astronomy since the Copernican revolution. The principle asserts that we do not occupy a special or privileged position in the universe. Earth is not the centre of anything. Our location in space and time is ordinary, typical, unremarkable. This assumption has been spectacularly validated by centuries of observations. Every time humans thought we were special, we turned out to be wrong. The Earth is not the centre of the solar system. The Sun is not the centre of the galaxy. Our galaxy is not the centre of the universe. The cosmological principle takes this trend to its logical conclusion. There is no centre, no special location, because the universe is fundamentally homogeneous and isotropic when viewed on large enough scales. This principle is so deeply embedded in modern cosmology that questioning it feels like stepping backward into pre-Copernican thinking. Yet the KBC void, if its interpretation as an exceptionally rare structure is correct, suggests that our location might be unusual after all. Not special in a Ptolemaic sense of being at the centre of everything, but unusual in a statistical sense of occupying a region that differs significantly from the cosmic average. This raises uncomfortable questions about observer selection effects. If intelligent civilizations can only arise in certain types of environments, then all observers will necessarily find themselves in those environments, regardless of how common or rare they are in the universe as a whole. This is the essence of the anthropic principle. Perhaps life requires galaxies to form with sufficient chemical complexity, moderate star formation rates, and relative isolation from disruptive events like galaxy mergers or close supernova explosions. Such conditions might be more common in voids than in dense cluster environments. If most observers live in voids, then finding ourselves in the KBC void would not be surprising, even if voids occupy only a small fraction of the universe's volume. We would be where we are because that is where observers can exist. This argument is philosophically controversial because it seems to explain observations by reference to our existence, rather than by reference to physical laws. It feels circular, unfalsifiable, and somehow unsatisfying even if it might be true. The void also raises epistemological questions about the limits of cosmological knowledge. If our location significantly biases our observations, how can we ever know what the universe truly looks like from a neutral vantage point? We cannot step outside our location in space to observe the cosmos from elsewhere. We are forever embedded within it, and our observations will always carry the imprint of our specific position. This does not make cosmology impossible, but it adds layers of interpretation and modelling that introduce additional uncertainties. Scientists must construct models of the universe that account for our location, and then extract universal truths from observations that are inherently local. This requires making assumptions about what is local versus what is global. What is a peculiarity of our environment versus what is a fundamental property of the cosmos. These assumptions can be tested against observations, but the tests themselves rely on further assumptions, creating a web of interdependence that can be difficult to untangle completely. The void also connects to debates about the nature of scientific realism. Are we discovering the universe as it really is, or are we constructing models that fit our observations without necessarily corresponding to underlying reality? The fact that competent scientists can disagree about whether the KBC void is a single structure, multiple overlapping structures, or an observational artifact shows how observations underdetermine theory. Multiple different models can fit the same data, especially when that data has significant uncertainties and systematic effects. This does not mean science is arbitrary, or that all interpretations are equally valid. Some models fit the data better than others. Some make testable predictions that can distinguish between alternatives. But it does mean that scientific knowledge, especially in cosmology, where direct experimental manipulation is impossible, is always somewhat provisional and subject to revision as new observations become available or new theoretical frameworks are developed. There are also implications for how we think about cosmic significance and meaning. For millennia, humans placed themselves at the centre of creation. The Copernican revolution dethroned us from that position, and subsequent discoveries continued the process of cosmic demotion. We are not even made of the same stuff as most of the universe. Dark matter and dark energy dominate, while normal matter is a minor component. Finding ourselves in an unusual location might seem like a step backward from this humility. But perhaps it is not about being special in any privileged sense, but about recognizing that the universe is more complex and inhomogeneous than our simplest models assume. The cosmological principle might be approximately true on average, but with significant local variations that matter for observers like us who exist in particular places. Accepting this complexity is not anthropocentric arrogance, but intellectual honesty about the messiness of the actual universe versus the tidiness of our idealized models. The void reminds us that science is a human endeavor, conducted by observers at a particular location and time, using instruments with particular capabilities and limitations. The knowledge we construct is real and valuable, but it is also situated and contextual in ways that we must continually work to understand and account for. This philosophical humility is not scientific weakness but scientific strength, acknowledging the challenges we face while working to overcome them through better observations, more sophisticated models, and deeper theoretical understanding. If we live inside a cosmic void, are there other civilizations facing the same cosmic isolation? This question connects the KBC void to one of humanity's deepest inquiries. Are we alone in the universe? The distribution of matter in cosmic voids has profound implications for where and how often intelligent life might arise, and it raises fascinating questions about what other civilizations might observe about the universe from their own unique vantage points. The conditions for life as we understand it require certain basic ingredients. Planets need heavy elements like carbon, oxygen, nitrogen, and iron, which are created inside stars and dispersed through space when those stars die. This means life can only arise in regions where stars have been forming for long enough to enrich the interstellar medium with these elements. In the early universe, when only hydrogen and helium existed, life was impossible. Several generations of stars had to live and die before the chemical complexity necessary for biology could emerge. Void galaxies tend to have lower metallicity than cluster galaxies, meaning they contain fewer heavy elements. This is a consequence of their slower star formation rates over cosmic history. Fewer stars means fewer supernovae enriching the interstellar gas with heavy elements. If rocky planets require a certain minimum metallicity to form, then void galaxies might produce fewer habitable worlds than galaxies in denser environments. This would make voids relatively barren of life despite occupying most of the universe's volume. However, the relationship between metallicity and habitability is not straightforward. While extremely metal-poor environments might struggle to form Earth-like planets, even modest metallicity may be sufficient once a threshold is crossed. Many void galaxies have metallicities similar to the Milky Way, just distributed somewhat differently. If the threshold for planet formation is lower than previously thought, void galaxies could host abundant planetary systems despite their overall lower metal content. There are also arguments that void environments might be better for life in some ways. Void galaxies experience fewer catastrophic events than cluster galaxies. In dense environments, galaxies collide frequently. These collisions can trigger intense starbursts that consume gas reservoirs rapidly, create bursts of supernovae that could sterilize nearby planets with radiation, and disrupt planetary systems through gravitational perturbations. Galaxy clusters also contain hot intracluster gas that strips gas from member galaxies, shutting down star formation and potentially affecting planetary atmospheres. Void galaxies evolve peacefully in comparison. They rarely collide with neighbours. Their star formation proceeds at a moderate, steady pace. Supernovae are less frequent but still occur regularly enough to enrich the interstellar medium. For a civilization trying to develop on a planet around a star in a void galaxy, the cosmic environment might be remarkably stable over billions of years. There would be fewer nearby gamma-ray bursts or supernovae to worry about. No galaxy mergers would disrupt the local stellar neighbourhood. The void would provide a quiet cosmic haven for long-term evolution. The isolation also has implications for how life spreads through space. Some theories of panspermia propose that life can be transferred between planetary systems on meteors or comets ejected from their home systems. In dense stellar environments, the distances between stars are small enough that this transfer might be feasible over cosmic timescales. But in void galaxies, where stars are more spread out and galaxies are isolated from neighbours, panspermia becomes less plausible. Each void galaxy would need to develop life independently rather than receiving it from elsewhere. If other technological civilizations exist in the KBC void, what would their cosmology look like? Would they discover the same truths about the universe that we have discovered? Or would their observations lead them to different conclusions? A civilization in a dense cluster would observe rich structure in every direction. Their sky would be crowded with nearby galaxies, easily resolvable even with modest telescopes. They would quickly discover cosmic expansion because they could observe many galaxies at various distances and measure the redshift distance relationship with high precision. For them, the Big Bang model would be natural and quickly accepted. The evidence would be overwhelming and obvious, but a civilization deep inside a void might struggle to understand cosmology. With few nearby galaxies to observe, measuring cosmic expansion becomes challenging. The void's effect on local measurements could confuse them, leading to incorrect conclusions about the universe's properties. They might develop alternative models explaining their observations without invoking cosmic expansion or dark energy, models that would seem bizarre to us but that would fit their limited data. They might also face philosophical questions about their isolation. Looking out at their empty sky, seeing only a handful of nearby galaxies and vast darkness beyond, they might wonder if they are alone in a small, finite universe. The truth, that they live in a vast cosmos containing hundreds of billions of galaxies, but most of them lie beyond their observational horizon, might be difficult to discover from their vantage point. They would need to develop incredibly sensitive instruments to detect the faint, distant galaxies at the void's edge and beyond. Conversely, if we are typical of void civilizations, then other intelligent species might also wonder whether their cosmological measurements are distorted by their location. They might also be measuring the universe from inside voids, seeing expansion rates that do not match the global average, struggling with their own versions of the Hubble tension. Perhaps this is a common problem for observers who develop cosmology. Most civilizations emerge in relatively quiet, isolated environments like voids, and most therefore face systematic observational biases that complicate their attempts to understand the larger cosmos. The search for extraterrestrial intelligence, SETI, has traditionally focused on searching for radio signals or other technosignatures from nearby stars. But if we live in a void with relatively few galaxies nearby, and if those galaxies have lower star formation rates and fewer heavy elements on average, then the density of technological civilizations in our cosmic neighborhood might be lower than in denser regions of the universe. We might be searching in a relatively empty part of the cosmic web, reducing our chances of detecting signals. On the other hand, the isolation might work in our favour. In a quiet void without the radio noise from intense star formation regions or active galactic nuclei, signals might propagate more cleanly across interstellar and even intergalactic distances. A beacon from another void civilization could potentially be detected across millions of light years with less interference than in a crowded cluster environment. The void's emptiness might make it easier for void civilizations to find each other, creating a sparse network of isolated but detectable technological species scattered through the underdense region. There is also the possibility that advanced civilizations might recognize the void's existence and use it for their own purposes. A void provides a vast, relatively empty volume of space, with minimal gravitational interference from large structures. This could be useful for certain types of mega-scale engineering projects or experiments. A sufficiently advanced civilization might even modify the void structure deliberately, creating signatures that could be detected by other civilizations. We might be looking for natural astronomical phenomena when we should be looking for engineered structures on cosmic scales. These speculations remind us that our understanding of life in the universe is still in its infancy. We have one example of life, Earth, and 0 examples of extraterrestrial technological civilizations. Extrapolating from this tiny sample to make predictions about the entire cosmos is fraught with uncertainty. The KBC void adds another layer to this uncertainty by suggesting that our local environment is unusual in ways that might affect both the prevalence of life and our ability to detect it. We are searching for signals while floating in a cosmic desert, and we do not yet know whether that desert is barren of life or whether it simply makes life harder to find. The coming decades will bring revolutionary advances in our understanding of the KBC void and cosmic voids in general. Multiple next-generation astronomical facilities are being built or planned specifically to address questions about large-scale structure, dark energy, and the nature of cosmic expansion. These instruments will transform void research from a niche specialty into a central pillar of observational cosmology. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in 2025 with the largest digital camera ever built for astronomy. Over 10 years, it will photograph the entire visible sky every few nights, creating an unprecedented time-lapse movie of the cosmos. The Legacy Survey of Space and Time, as the project is called, will discover tens of billions of new astronomical objects, including hundreds of millions of new galaxies, that will extend our maps of cosmic structure to greater depth and detail than ever achieved. For void research, Rubin Observatory will provide the most complete census yet of galaxies within the KBC void and surrounding regions. By measuring accurate positions and distances for millions of galaxies, astronomers will map the void's density profile with exquisite precision. They will trace its boundaries, identify substructure within it, measure how it connects to the surrounding cosmic web, and compare it in detail to voids in other parts of the universe. This will allow definitive tests of whether the KBC void is genuinely as unusual as current observations suggest, or whether it is one of many such structures that we have simply not yet found. The Euclid Space Telescope, launched in 2023, is specifically designed to study dark energy and dark matter by mapping galaxy distributions and gravitational lensing across large swaths of the sky. Euclid will measure distances to billions of galaxies using multiple independent techniques, allowing cross-checks that reduce systematic uncertainties. For void studies, Euclid will provide precision measurements of void shapes, density contrasts, and velocity fields. These measurements will test whether voids behave as standard dark energy models predict, or whether there are anomalies indicating new physics. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will survey larger areas of sky than Hubble with similar resolution. Roman's wide field of view makes it ideal for mapping large-scale structure and conducting supernova surveys that trace cosmic expansion history. The telescope will discover thousands of new Type Ia supernovae at various distances, allowing researchers to measure how the apparent expansion rate varies with distance and cosmic epoch. This will provide definitive tests of whether the local Hubble constant is indeed inflated by the void, or whether the tension requires alternative explanations. Ground-based spectroscopic surveys are also advancing rapidly. The Dark Energy Spectroscopic Instrument completed its main survey in 2024, after measuring redshifts for over 40 million galaxies and quasars. The data has already provided the most precise baryon acoustic oscillation measurements to date, confirming that a void model fits the observations far better than models without a local underdensity. As DESI data continues to be analysed over the coming years, researchers will extract increasingly refined measurements of the void's properties and test theoretical predictions in unprecedented detail. Future radio telescopes will contribute unique perspectives on void structure. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's largest and most sensitive radio telescope when completed in the 2030s. SK will map neutral hydrogen gas throughout the nearby universe, revealing the distribution of matter in voids where few galaxies exist, but diffuse gas remains detectable. This will show how voids connect to filaments through tendrils of gas, and how matter flows from voids into denser structures over time. Gravitational wave astronomy, still in its infancy, will eventually contribute to void studies in unexpected ways. As gravitational wave detectors become more sensitive, they will observe mergers of black holes and neutron stars throughout the local universe. The distribution of these events traces the distribution of galaxies and star formation, providing an independent probe of cosmic structure that does not rely on electromagnetic observations. Gravitational waves from mergers in voids versus dense regions might have subtly different properties due to the different evolutionary histories of galaxies in these environments. Theoretical work will advance in parallel with observations. Improved cosmological simulations incorporating better dark matter physics, more realistic baryonic processes, and higher resolution will test whether voids like the KBC void can form in standard lambda cold dark matter, or whether they genuinely require modified gravity or exotic initial conditions. Simulations are already reaching unprecedented size and detail, modelling cubic volumes billions of light-years across while resolving individual galaxies. These simulations will generate predictions for what future observations should see if various theoretical models are correct. Machine learning and artificial intelligence are beginning to transform astronomical data analysis. Neural networks can identify patterns in massive datasets that traditional statistical methods might miss. They can classify galaxies, detect anomalies, and even predict properties of unobserved structures based on training from simulations. Applied to void research, machine learning could discover subtle features in the density and velocity fields that reveal how voids form, evolve, and affect their surroundings. AI might even suggest new theoretical frameworks by identifying patterns that human researchers have not yet recognized. Within a decade, we will know the KBC void's properties to percent-level precision. We will know its exact size, depth, and shape. We will have detailed maps of its velocity field and density profile. We will understand how it affects our observations of cosmic expansion, the cosmic microwave background, and large-scale structure. We will know whether it is a rare statistical fluke, an indication that structure formation proceeds more vigorously than standard models predict, or evidence for modified gravity. The void will either be confirmed as the explanation for the Hubble tension or be ruled out definitively, forcing cosmologists to seek alternative solutions. Whatever the answers, they will reshape our understanding of cosmic structure and our place within it. The void has already challenged fundamental assumptions about the universe's homogeneity and our ability to make unbiased cosmological measurements. As research continues, it will either reinforce those challenges, forcing us to revise our theories, or it will teach us how to properly account for local structure in ways that preserve the standard cosmological framework. Either outcome represents a major advance in our understanding of the cosmos. We are inside a cosmic hole 2 billion light-years wide. This is not metaphor or speculation. This is observation backed by multiple independent lines of evidence from galaxy counts, velocity measurements, baryon acoustic oscillations, and cosmic microwave background studies. The KBC void is real, its effects are measurable, and its existence challenges fundamental assumptions about cosmology that have guided our understanding for decades. Whether it explains the Hubble tension remains a subject of active debate, but the evidence increasingly points in that direction. Recent observations from 2024 and 2025, including data from the James Webb Space Telescope and the Dark Energy Spectroscopic Instrument, have strengthened the case that we are measuring the universe's expansion from inside an unusual location. The measurements are not wrong, they are local, and local measurements in a void do not necessarily represent global properties. Whether the void requires modified gravity or simply represents a statistical fluke in standard cosmology is also unresolved. MOND and other alternative theories can explain the void's existence and properties more naturally than lambda-cold dark matter, but they face other challenges. The debate continues, with researchers on both sides making valid points. What is certain is that the void exists and that it affects our observations in measurable ways. What does this mean for our place in the universe? It means we are cosmic castaways, drifting through a desert of space that most of the universe does not resemble. Our measurements of cosmic expansion, the universe's age, the properties of dark energy, all of these may be systematically biased by our unusual location. Every number in cosmology textbooks might need revision once we properly account for the void's influence. We are not measuring the universe as it truly is, we are measuring it through the distorting lens of our local environment. This is simultaneously humbling and exciting. Humbling because it reminds us that our view of reality is always limited by our vantage point. We cannot step outside our location in space and time to see the universe from a neutral perspective. We are embedded in it, and our observations will always carry the imprint of where and when we happen to exist. Exciting because it means we have new physics to discover. The void gives us a natural laboratory for testing theories of gravity, dark energy, and structure formation under extreme conditions. The universe is far stranger than we imagined, and our place within it is more unusual than we ever suspected. We live in a hole, and that hole is teaching us profound lessons about the nature of reality. As observations continue to improve and our understanding deepens, we will either confirm the void as the solution to cosmology's biggest puzzle, or discover something even more surprising lurking in the data. The coming years will bring new surveys, new telescopes, and new measurements that should resolve many of the current debates. The Euclid Space Telescope, the Vera Rubin Observatory, and next-generation instruments will map the universe with unprecedented precision. They will either confirm that we live in a statistical outlier, requiring us to accept that Earth occupies a genuinely unusual cosmic address, or they will reveal that large voids are more common than standard models predict, forcing us to revise our understanding of structure formation and possibly gravity itself. Either outcome represents a revolution in cosmology. Either we are special, violating the cosmological principle that has guided astronomy for centuries, or we need new physics to explain how the universe creates its larger structures. The void has already transformed our understanding by revealing that the cosmos is not as uniform as we assumed. What other assumptions will it force us to reconsider? What other hidden features of reality might we be missing because we measure from inside this hole? These questions will occupy cosmologists for years to come. The KBC void has opened a window into the universe's deepest mysteries, and we are just beginning to peer through it. We are inside a giant cosmic hole, and the view from here is teaching us that the universe is far more complex, far more dynamic, and far more surprising than our simplest theories ever suggested. We measure the cosmos from the edge of a void, and in doing so, we are discovering that reality itself may not be quite what it seems. If this journey through the void has opened your eyes to the strange and wonderful universe we inhabit, hit that like button and subscribe for more deep dives into the cosmic mysteries that surround us. The universe is vast, strange, and full of secrets waiting to be discovered. And sometimes, the biggest secrets hide in the emptiest places.